This is Bob Capetta from the University of Illinois at Chicago, and this lesson is a partial fraction expansion example for distinct linear factors. So we have three factors in the denominator, all linear, all equations of lines. We're going to rewrite this as a sum of three fractions, something over x minus 4 plus something over x minus 2 plus something over x plus 1. And then our goal is going to be to solve for a, b, and c. Our first step is to write this vertically, and we're going to build common denominators. So we want to change all of these fractions to have the denominator x minus 4, x minus 2, x plus 1. The question then is, how do these numerators change? Well, x minus 4 was there before. The denominator is multiplied by x minus 2x plus 1. Multiply the top by x minus 2x plus 1. So this will be a times x minus 2x plus 1. Similarly for the next two. So we see the a x minus 2x plus 1. How did this one work? X minus 2 was there before. X minus 4 is new, put it on top. X plus 1 is new, put it on top. How did this work? X plus 1 was there before. X minus 4 is new, it's on top. X minus 2 is new, it's on top. If you would reduce these fractions, notice that the terms would cancel, x minus 2, x plus 1, leaving a over x minus 4. X minus 4 cancels, x plus 1 cancels, leaving b over x minus 2. X minus 4 cancels, x minus 2 cancels, leaving c over x plus 1. So we have equivalent fractions. Our next move is to multiply these out. So let's multiply the two binomials first. So x minus 2 times x plus 1, x squared minus 2x plus 1x minus 2 becomes x squared minus x minus 2. X squared minus 4x plus 1x minus 4 becomes x squared minus 3x minus 4. X squared minus 4x minus 2x plus 8 becomes x squared minus 6x plus 8. Remember, our goal is to solve for a, b, and c. So how are we going to do that? Let's distribute that ax squared minus ax minus 2a, check. Bx squared minus 3bx minus 4b, check. Cx squared minus c times 6x, 6cx plus 8c, check. We've written it that way. Now, what are we going to do with this? We're going to go ahead and recognize that these numerators have to add up to the same thing. So the first numerator is x squared minus 11x plus 48. It has to equal this numerator plus this numerator plus this numerator. So we're here, and let's go collect the like terms. Let's get all the x squareds together. What would they be? Ax squared plus bx squared plus cx squared. Get all the x's together, negative ax minus 3bx minus 6cx. All the constants together, negative 2a minus 4b plus 8c. Factoring out the x squared here, factoring out the x there. Now you'll see that the coefficient of the x squared term on the right side is a plus b plus c. On the left side we have x squared, or 1x squared. So a plus b plus c has to equal 1. And similarly, the x terms, negative a minus 3b minus 6c has to equal negative 11. Negative 2a minus 4b plus 8c has to equal 48. So knowing that, we have a system of three equations and three unknowns, which is a fairly long process to complete, but not terribly difficult. So we have to solve for a, b, and c. How are we going to do that? I'm going to choose to eliminate variables. So I have three equations, equations 1, 2, and 3. My goal is to pick two of them at a time and eliminate the a's. So I'm going to pick equation 1 and equation 2, eliminate the a's. Pick equation 1 and equation 3 and eliminate the a's. You'll see when I do that, the resulting equation has only b's and c's. So here we go. Here's equation 1 and equation 2. To eliminate the a's, we add these two equations together. A plus negative a, 0a. That's gone. B plus negative 3b, negative 2b. C plus negative 6c, negative 5c. 1 plus negative 11, negative 10. So the resulting equation there is negative 2b minus 5c equals negative 10. So we want to do this again with equation 1 and 3. Now you could do equation 2 and 3. Any pair works. But I'm choosing equation 1 and equation 3. To eliminate the a's, I want all the a's to cancel out. I have a negative 2a here. Let's multiply the top equation by positive 2. Distributing that, 2a plus 2b plus 2c equals 2. When I add those together then, the 2a plus the negative 2a will go away. 2a plus negative 2a is 0a. 2b minus 4b, negative 2b. 2c plus 8c, 10c. 2 and 48 is 50. So negative 2b plus 10c is 50. Now I have an equation with two unknowns, b and c here, b and c here. Once that's the case, then I can go ahead and solve for b and c. So indeed, solve for b and c using this equation and that equation. So here we go. How are we going to do that? Multiply the first equation by negative 1. That'll make that positive 2b. The second one is negative 2b, and those will cancel nicely. So 2b plus 5c equals 10, distributing the negative 1. The other equation is negative 2b plus 10c is 50. 2b negative 2b cancels. 5c and 10c is 15c. 10 and 50 is 60. 15c is 60. So what is c? C is 4, dividing both sides by 15. Now I've got to go ahead and solve for b. So I plug this c into one of these two equations. Choosing the first one, if c is 4, negative 5 times 4 is negative 20. Adding 20 to both sides, we get negative 2b is 10. Dividing by negative 2, b is negative 5. So what's our next move? We have b and c. We had 3 equations and 3 unknowns. I'm going to pick one of those equations, plug in b and c, and solve for a. So what were those original equations? Here they are. I can pick any one of them. I know what b and c are. I'm going to plug b and c into one of them to solve for a. But it doesn't matter which one you choose, you'll get the same a in each case. Choosing the first one looks like the simplest. So replacing b with negative 5 and c with 4, we get this. Negative 5 plus 4, negative 1. So a minus 1 is 1. And of course, if that's the case, a is going to equal 2. So we have a, b, and c. Where do we put those? We've got to look at our original rational function. Remember, it was a over something plus b over something plus c over something. Let's go ahead and plug in those values and then begin the process of doing the integral. So there's our a, there's our b, there's our c. Here's our original rational function, and we asked to write it this way. Now if that's the case, we change a with 2, replace b with negative 5, substitute 4 in for c. We wanted to integrate this rational function on the left, and now all we have to do is integrate the rational function on the right. The integral of the sum is the sum of the integrals, and that will make that relatively easy to do. So we're going to take the integral of the first piece plus the integral of the second piece plus the integral of the third piece. And then we can factor out these constants. 2 comes in front of the integral sign, negative 5 comes out, 4 comes out. And at this point we have to do some substitution. So how about u is x minus 4, v is x minus 2, w is x plus 1. If u is x minus 4, the derivative with respect to x of u is the derivative with respect to x of x minus 4. So du dx is 1, du equals dx. Similarly, for our second case, v is going to equal x minus 2. ddx of v is ddx of x minus 2. dv dx is 1. dv equals dx. And of course, the last one is done the same way. If w is x plus 1, ddx of w is ddx of x plus 1. dw dx is 1. dw is dx. This becomes u, that's du. This becomes v, that's dv. This becomes w, that's dw. So just about ready to finish. There's all of my change of variables. Here's the equation we were left with. So replacing x minus 4 with u, dx with du, x minus 2 with v, dx with dv, x plus 1 with w, dx with dw, we get this. Integral of 1 over u is natural log absolute value of u. Integral of 1 over v, natural log absolute value of v. Integral of 1 over w, natural log absolute value of w. And then to finish the problem, just replace u with x minus 4, v with x minus 2, w with x plus 1. And there's our final solution, and that will conclude this example.